prosper. Kinetic energy, 252I, whatever. Good luck figuring out what the first part was about. Okay, so if I drop an object from the top of an object, it's going to fall and hit the ground. So far, so good? Okay. How do I figure this out? Velocity is v naught plus at. A is simply g, right? It's our acceleration of gravity, the dropping situation. But I don't know t, so that's not going to help me out. Still crying about that. So now I move forward. It wouldn't work anyways, right? Because I need my distance formula, right? So we go y equals 1/2 at squared plus v naught t. Agreed on that one? How far am I going to fall in this case if the height is h? H equals 1/2 acceleration 9, g, t squared plus what's the initial velocity? Dropped object 0, so that goes away. Now, what's interesting is we know this, the back, we know this is the form of potential energy, correct? So if I can figure out what g is and h is in terms of v, I could actually figure out the other side of the equation, couldn't I? Couldn't I? What do I have to get rid of, though? What clearly is not belonging. What? T. And we know T is as the enemy of energy because if we have a time problem, energy pretty much is useless. Okay, so now I'm going to go, okay, T. So I'm going to go ahead and write V over G is equal to T. Isn't that exciting? And then I take it, I'm going to plug it in over here. And I'm going to go H equals 1/2 G, V over G squared. So far, so good? All right. Then I write H equals 1/2 G. I've got V squared over G squared. One of these G's cancels out, correct? If I move the G to the other side, I get GH equals 1/2 V squared. With me? So if the energy before is equal to the energy after, then the energy will be equal to M, and then GH is 1/2 V squared. And so the kinetic energy of any object, this is the part you write down, is 1/2 mv squared. Okay? So energy just simply by moving is going to equal to 1/2 your mass times the velocity you're at squared. Now, go ahead and do those two example problems down there. Let's go ahead and do example problem number 2. I guess it is 1 and 2 at the bottom of that page. Is that the right answer? Yeah.
So, Mr. Resney.
Yes.
If potential energy is equal to kinetic energy, couldn't you just solve for potential energy and that's the same as kinetic energy?
Yes. If at one point it has potential, it's all converted kinetic. It's the same thing. That's what we did over there. That's how we found the kinetic energy, even though we don't even know what kinetic energy was. But that's not the most powerful statement. And we'll get to what powerful statement in just a second about what he did over there.
Are you going to ask us about, like, after 4 seconds, how much potential energy is there and how much?
That's not really a great energy question. Why? Because it's got time in it. Now, I might ask if it's fallen this distance, what's the change of potential energy? That's a good energy question. But time is the enemy of all energy. Time and friction are the two that can be problems not working. Everybody got the first one done? Happy? Oh, I have to do the second one. My bad. First one, you guys have the first one done? What's the answer? Second one. First example, number 1. 2,250. Everybody agree with that? Jules? Okay. And so then I might back up and say, all right, so the potential energy is going to be what? 100 joules. Right? Because if I have that much energy when I hit to the bottom of the cliff, how much potential do you have at the top? 100 joules. And if I had 100 joules, how high is the cliff? Yes, ma'am. What'd you do? You did D? Isn't this nicer though?
Yeah.
And I'm gonna make that point expressly in a second. But yes, it should work. Did you get the right answer?
Yeah.
Good. All right. Stephanie made a great point. Can I use the old-fashioned way to do it? Yes. Almost every energy problem we're going to do this chapter, you could have done. Daniel, voice down a little bit. Almost every energy problem we've done this chapter, you could do another way. So the advantage of energy, that's easier. Let me make that point. Do you remember that problem over there Mr. Fox did? Mr. Fox was forced to solve for the speed at which it hits the ground. How much kinetic energy does the object have? 1,800,000 joules. So kinetic energy is equal to 1/2 mv squared, right? Kinetic energy is 1,800,000 joules. That's equal to 1/2. What's the mass? 65 v squared. Solve for v. So we solve for v, so we can figure out this 2/34. I mean, it's meant really solve for v. So we solve for v.
235.3.
So there's a little bit of rounding issue. Good deal. Make sense? So which way is easier to do it? The way Ms. Fox did D before he knew about it? Or the way I just did it?
No, it's the same. We just didn't round it up.
Oh, okay.
We rounded up to 235.
All right, fair enough. Which way is easier? Yeah. And that's where the energy is really worth doing, is when it makes your problem that easy rather than that easy. Does that make sense? That's what we want to do. All right, let me give you some kinetic energy problems for you to play with. Pause this.
So we would have been like super